So it's my pleasure to introduce our colleague from mathematics department, Cristian Barbarosie. He's a professor and he's an expert in numerical methods. In particular, he develops mathematical algorithms for optimization of material properties like elastic properties and sound propagation properties using advanced numerical novel algorithms. He also developed a software, free, open source C++ for three-dimensional domain discretization and finite element methods. And today he will speak about one part of his research, homogenization of material properties is from the point of view of sound propagation. Right?
Thank you, Nicola. Hello. So I will talk about homogenization theory and Bloch waves. Homogenization theory is about describing effective properties, effective mechanical properties of bodies or media with small inhomogeneities. So I shall start with a very simple equation, which is similar to the Laplace equation, except that you have a coefficient k here. So if you consider that k is constant, you can put k outside the divergence and you get the Laplacian equation. So you have some boundary condition, narrow boundary condition, different boundary condition. And this is the same equation written in coordinates. So you can imagine here that u is a scalar function. I imagine it as a temperature. If you imagine u as a temperature, then k is a sort of conductivity of the material, of the body. And g is heat flux entering on the Neumann boundary. But we will be mainly interested in the case when k is not constant. K varies from point to point, so you cannot do this. So when k varies, you have here different color, you have two different values of k. So k depends on x. But not only that, you suppose you have a small scale, so you suppose that the inhomogeneities are small. Mathematically speaking, you have to have a small parameter. You have to imagine a sequence of coefficients, a sequence of functions, k epsilon. Epsilon is some quantity going to 0. And k epsilon is a sequence of functions which describe non-homogeneous conductivities, for instance. So you have a sequence of elliptic problems, a sequence of Laplace-like problems with the same source. This is a heat source in the bulk. This is a heat source entering on the boundary. And you want to describe the macroscopic behavior in the limit, of the limit problem. You have to imagine how the limit problem would be. This is the goal of homogenization theory. And you can do the same with linear elasticity, for instance, which means you have a vector unknown function u, which is the elastic displacement. You have a Hooke tensor C, and you have Dirichlet boundary conditions, for instance here, and Neumann boundary condition, which in this drawing is force 0 here, and some applied force here, which is G. And when you write the linear elasticity equation, by the way, if you have any questions, feel free to interrupt me. When you write equations of linear elasticity, usually you use the strain tensor, which is the symmetric part of the gradient of the vector function u. I will close this document. But due to the symmetries of the Hooke tensor, which by the way is a fourth order tensor, due to its symmetry you can put the gradient here, it doesn't make any difference. And this is the same equation written in coordinates. You have here components of u is a vector function, partial derivatives, and these are the components of the fourth order Hooke tensor. And again, you want to look at the non-homogeneous bodies, so the Hooke tensor depends on x, and this depends on a small parameter epsilon. And so you consider a sequence of problems, a sequence of linear elastic problem, and you want to describe the macroscopic behavior in the limit. So what we do here is, first of all, there is a mathematical result which says that the limit exists. You can describe the limit. There is something which you can call CH, which you can call homogenized Hooke tensor. And the definition of the convergence, so there is a convergence. It's a strange kind of convergence. The definition of this convergence is like this. If you look at the solutions U epsilon of the problem before passing to the limit, and you say, this elastic tensor, this sequence of elastic tensors converges, H converges to this effective elastic tensor, this effective Hooke tensor, if the solutions of this problem converge to the solutions of this problem. So you define the convergence of the tensor through the weak convergence of the solutions, U epsilon. So the U epsilon converges weakly in H1 to the solution of the so-called homogenized problem. And you say, well, if this happens, then this is the effective behavior of the limit body. So this is a very abstract definition of convergence. It's interesting from the mathematical point of view. Doesn't have much value, much practical value. But anyway, you can prove that this is a true convergence. There is a topology on the set of all Hooke tensors, of all possible Hooke tensors, which are limited by two constant alpha and beta in a certain sense. And it has local character. So what happens in a small zone of the body doesn't depend on the boundary condition. So that the H limit, the tensor, the homogeneous tensor, doesn't depend on the boundary conditions and doesn't depend on what happens far away from that zone. It's local. It's a local convergence. It is measurable, and we have a compact space, which is useful when you want to prove the existence of certain solutions, for instance, in optimization or optimization problems. Okay, however, this is not useful from the practical point of view. It doesn't give you any way to compute, effectively compute the H limit. This is because we didn't assume any kind of, we didn't explain how these inhomogeneities are distributed. If you add one more hypothesis, which is the periodicity hypothesis, then you can say more, you can make computations. So you say, well, it's not just any mixture, that it's periodic. So it comes from a pattern, C star. So C star is some sort of pattern Hooke tensor. And then you make a zoom, and you obtain this kind of pattern with the size epsilon. So this is the size of the inhomogeneities. And you assume that this pattern Hooke tensor, which is defined on Rn and it takes values in the space of fourth order tensors, it is periodic. Periodic means that it is invariant to certain translations. So here's a translation, and you call some function, some object periodic, if it is invariant to translations. Translations belonging to a certain set of translations, which is a group. Algebraically, this is a group of translations. And you can consider different periodicity patterns by choosing different groups of translations, different periodicity groups. For instance, you can have rectangular periodicity. So these dots here are trying to suggest a group, a lattice. It's a lattice in R2. So this is a group, an algebraic group generated. It could be generated by these two vectors. So if you take these two vectors and you make all linear combinations with integer coefficients, you obtain these dots, all these dots, all the lattice. But beware that the generators are not uniquely associated to the lattice. The same lattice could be generated by a different set of generators. You can have these two generated, they produce exactly the same periodicity group. And if you want to consider a periodicity cell, you could have this periodicity cell or this one, doesn't matter. So there is a certain lack of unicity. The same lattice could be represented by different cells. Or you can have different periodicity arrangements. For instance, this is a nice one. We call it hexagonal because one possible periodicity cell is a hexagon. So you have here this lattice, you have here this possible pair of generators. This is another pair of generators. They define exactly the same lattice, exactly the same group. And you have here different possible choices of the periodicity cell. So you can work, if you want to do computations, you can work on domain like this. You can choose your domain, but you have to be careful with how these periodicity, how the lattice corresponds. For instance, here you can choose a rectangular cell, but you have to see that this point corresponds to the middle of this one. Unlike in the square case, here this point corresponds to this one. So you have to be careful. And you can choose even very strange periodicity cells like this. They don't have to be straight. The lines don't have to be straight. So, for a periodic mixture of materials, independently of the periodicity group that you choose the periodicity group G, and then what you do is you look at your mixture and you make a zoom around a certain point. You make a zoom with power 1 over epsilon. And so the small inhomogeneities, which had size epsilon, you make a zoom, they become size 1, for instance. So when you do this, you obtain a new problem. When you do this zoom, you get here the pattern Hooke tensor. You get an equilibrium equation which holds the entire Rn, because in the entire plane, if you want, imagine n equal 2, in the entire plane. Because when you make this zoom with power 1 over epsilon, and epsilon goes to 0, so this means that your boundaries go far away. So in the limit, the boundaries disappear from your analysis. You get a problem which is set on the entire plane or the entire space, and there is no boundary. The boundaries are blown away. And you have to assume, you need to assume that the solution of this equilibrium equation has this structure. It is linear. The main part is linear, and there is a periodic perturbation. So you have a linear function, and you assume that this linear function is perturbed, the perturbation being periodic. So saying that this perturbation is periodic can be written in different ways. Can be written like this. By the way, I have here an example of this is a periodicity cell, this is a finite element mesh, and this is an example of level lines of a function which has a main part which is linear. See, this is linear like this, and it has a perturbation which is periodic. Well, because basically you take mu epsilon, so you go back here, and you say, I want to make a zoom around a certain point here. So you look at your u epsilon, and you approximate u epsilon by its tangent plane around that point. So this linear, so you analyze the linear approximation of u epsilon, and this is why you analyze the linear part, which is this one, and you assume there is a periodic perturbation. So this is the linear part, which you can consider that it's the tangent function to u epsilon at that point. And there is a perturbation, a periodic perturbation. So this is how such a function can look like. These are the level lines of such a function. This is a finite element mesh. By the way, when I solve this problem, I only discretize the periodicity itself, of course. I don't discretize the entire plane. So this finite element lives on this domain. This is the domain. By the way, this should be square. The projector is deforming the proportions. I'm not sure if we could correct that. It should be a square. Maybe there is a way to correct that, but the projector is deforming this. And these finite elements, these triangles, are periodically repeated outside the periodicity cell. which means that this vertex, for instance, is exactly the same with this one. In my computer, there are only one vertex. You see here more than one, just for visualization purposes. So in the computer, this vertex is the same with this one. And if you look at this one, for instance, it's the same with this one and with this one. Here is not perfect. The drawing is not perfect. So it should be the same. So the finite elements that I use for solving the elliptic problem they live on this periodicity cell, and they are subject to periodic boundary conditions. Anyway, so after you solve this problem, by the way, A is a datum here, so you choose A to be a matrix. This is the linear part of your unknown U. You can imagine this like a uniform stretch, a uniform deformation, elastic deformation, if you look at elasticity. Then you say, actually this is the mean value of the gradient of the solution that you compute here. And if you look at the mean value of the stress, so this is, you can say this is the mean value of the strain, and you define the mean value, you compute the mean value of the stress, and you say that the homogeneous tensor is exactly the quantity, the Hooke tensor, which relates this effective strain to this effective stress. And the relation is this one. So this is a possible definition of stage. It's a computational definition. This is a way to compute effectively in the computer the homogenized behavior, the homogenized Hooke tensor. So you take several different effective strains, you solve this problem for several different matrices A, and for each effective strain, you compute the associated effective average stress, and you define the homogeneous tensor through this equality. Or if you prefer, you define it through this equality, which is a sort of energy. This is a sort of product between strain and stress, which is a sort of energy. So you can define it like this. It's perfectly equivalent. Now, it's not that obvious that you can also do like this. This equality is not obvious. It has to be proven mathematically. And it's nice that you can do it like this. So you can compute the average of the energy in your periodicity cell. This is the periodicity cell. And this gives you the average, the energy associated to the homogenized, to the effective Hooke tensor.
I'm not sure this integral
This is the average value. Integral with a bar means average value. This means integral divided by the area of y, of the dominant integration. So it's average. So you just divide by the volume of y, or by the area of y. Now, all that I have presented are static. I will go back now. This is static, has no time. So this is the equilibrium equation, okay? So if you want to study dynamics, things get more complicated. For instance, if you want to look at waves, things get more complicated. So let us look at waves. Suppose you have an elastic body, but it could be something different than elasticity. It could be an electromagnetic wave. So I have mainly worked with this case, which is a pressure wave, where you just have, it's like in water, it's a pressure wave. So you have the same sort of body with microscopic details, with small details, and here they are already periodic. And you consider an incident wave. You consider it stimulated and the wave propagates inside, and you want to describe its propagation. So these are the equations that describe the propagation of an acoustic pressure wave. This is an elastic wave, which is quite similar, but it's more complicated because you have the elastic tensor. This should be C. This is the Hooke tensor. Or you could have some electromagnetic wave. The point is that these numbers, C or this Hooke tensor, they are not constant. They depend from point to point. They vary in the body. You have, for instance, one value here, a different value there. Or you could have void here. So these coefficients, these material coefficients, they are not homogeneous, they are not constant. They vary in a periodic manner and at a small scale, all these ones. In order to study such problems, you would like to get rid of the time dependence. And you get rid of the time dependence by assuming that the wave has a special structure. It is monochromatic. It has a given angular frequency omega, and so this is the time dependence. So you isolate the time dependence from the dependence in space. This is a classical trick for studying wave propagations when you prescribe the frequency. So when you prescribe the frequency and you assume that the wave has this structure, then the time disappears, but the problem becomes different. You have here a term where the frequency, the angular frequency appears, or here, or here. So you get a static product, no time, but it's a sort of eigenvalue product. So we have here multiplying with the very same U. So U is your solution. U is the profile describing your wave. So it's an eigenvalue problem. You assume periodicity, and you assume that the period is small. And now, when you do the analysis, you are led to two different cases. You want to describe how the wave propagates in the limit. In the limit means when the inhomogeneities go to zero, they become so small that you cannot distinguish them. And you want to give an average description of how the wave propagates. And you are led to two cases. The periodicity cell can be small when compared to the wavelength. If this is the case, then the classical homogenization applies. You can homogenize, and you can replace this material, this not homogeneous material, by an effective homogeneous one. And the wave propagates as if the body was homogenized, had constant coefficients given by a homogenization theory. So this case is solved by classical homogenization theory. The second case is when the periodicity cell is comparable to the wavelength. And here things get complicated. Homogenization theory does not apply anymore. So here you have to go back and build again the whole theory. And you make the zoom, as I told you, and you add the hypothesis. Remember the hypothesis, I will write it on the blackboard. In the homogenization theory, we had the hypothesis that our solution was like a linear part plus a periodic perturbation. This was sort of a tangent function to the unknown U epsilon. Here you have, in order for computations to work, you have to assume a different expansion, a different structure. So you assume that there is a plane wave, this is a plane wave, multiplied by a periodic perturbation. So it's a plane wave which is perturbed, but it's not like this. This is a natural operation for waves. The product, the complex product is the natural operation for wave theory, not the sum. So here you have a leading term, a main term, which is a plane wave with a value vector k, and multiplied by a periodic perturbation, which is the equivalent to saying that your unknown u, has this behavior when you make translations. When you make translations, in this case, when you make translations, you have something that x plus v, this is the translation, you have something like this. So this is equivalent. Saying that phi is periodic is equivalent to saying that u behaves like this when you make a translation. Here, when you make a translation, you get a product. Yeah, let us put G. Doesn't matter. Could be G. G belongs to the periodicity group. And you get a new kind of cellular problem, and you can make computations. You can compute eigenvectors and eigenvalues of this problem. So, your unknown is defined in the entire space, but actually you can analyze it only on the periodicity cell because it has this structure, this periodicity behavior. And this is a sort of equilibrium equation, but now with this part here, which turns it into something like an eigenvalue problem. So the function C is the material coefficient. It contains information about the geometry of the homogeneities. And as usual, for eigenvalue problems, for any given, not the datum is K. Here, A was a datum of the problem. You choose different A's, and for each A, you interpret A as effective strain, and you associate the effective stress, and this is how you define the effective Hooke tensor. Here the datum is K, so you take different plane waves, different vector waves, and you solve this problem for a given K. And for any given K, you obtain a sequence of eigenvalues as usual, because it's an infinite dimensional problem. So it's similar to Laplacian, but it's an eigenvalue problem. So for each fixed vector wave K, you get different manners of the wave propagating with that vector wave. But you could also reverse the question. If you choose omega to be the frequency, the angular frequency, can you find a vector such that the propagation is like this? And the answer is surprising, because sometimes for certain geometries, for certain microgeometries in the cell, there is no solution, there is no K associated to that omega. So you obtain band gaps. So this should be circles. So we made computations for acoustic wave traversing, crossing through a matrix made of epoxy and with hard inclusions. And the main computation. This is the first eigenfrequency for different Ks. This axis describes the wave vector K. And this is the first eigenfrequency, this is the second eigenfrequency, this is the third one, and you have a gap here. So you have a region where the wave does not propagate, which is what we are interested in, right? And you can then manipulate the geometric characteristics of your inclusions, of your periodic inclusions, and you can enlarge, or at least try to enlarge the gap. Here you see a much larger gap with larger inclusions. Now, the wave vector K, when you analyze, you don't have to go to the entire plane. So initially K is something in R2, but actually you can limit it, otherwise the analysis becomes impossible, because you can think like this. You have a periodicity group, which I call G, and you define a dual group, which is the vectors having these properties. And so these are the vectors whose inner product are integer. This is a typical example of a periodic function. If you put here as wave vector something in the dual lattice, then you get a periodic function. And you can define something called the viewing zone. So this is the the direct group, this is the periodicity group. This is the corresponding generators in the dual group, in the dual lattice. And you say that, and you notice that if the difference between two wave vectors is in this lattice, then the corresponding Bloch problems are the same. There is no difference. So this is why you don't have to analyze K. You don't have to let K to go to all R2. You only need to analyze a cell, a periodicity cell in the dual lattice. So instead of analyzing all vectors, you look for all K's in a periodicity cell in the dual lattice. And then, if you assume some symmetry in your geometries, for instance, here we have analyzed geometries which are very symmetric. This is a circle, although it doesn't look like, and this is a square. So this is very symmetric. Due to the symmetries, you can reduce even further. You can cut this in half. You only analyze a triangle, half of the cell, and this is called. Actually, I think it's less than half. I think it's a quarter. I'm not sure right now. Anyway, this is called the BUE triangle. So it's either half of the cell or the quarter of the cell. In the dual group, it's called BUE triangle. And then, yes. Yep.
The examples that you gave, the examples, the previous examples, these ones, you have you have this black region and the gray region.
Yes, this is epoxy and this is some hard inclusion, some metallic inclusion.
So you have different C's for
Yep.
these two regions.
Yes, that's it. We have two C's. Mm-hmm.
And this special relation, they are for this non-uniform system, already homogenized. These results are.
Sorry, I didn't get the question.
So this spectrum, frequency
Yes.
versus K, this is obtained for this given geometry, or is it homogenized result?
It's already homogenized. It's already passed to the limit.
Okay, this is
So-
the limit already.
So if you're asking what's the size here, I don't know what the size, because it already goes to zero, but I assume that the size is the same order of magnitude with the wavelength. So it's ambiguous, because if you say I'm bombarding the body with an exterior wavelength or with an exterior wave, and it has a certain wavelength, then this should be equal or same order of magnitude with that wavelength. Okay, so it's not homogenized in the previous sense when we said the size goes to zero. Here, either you say you have two choices. Either you say this size goes to zero, and the stimulating wavelength goes to zero with the same speed, which is not very interesting from the physical point of view. Or you say, no, you have a stimulating wavelength, and this is the same size, the same order of magnitude. So you cannot shrink it to zero like in homogenization theory, like in usual homogenization theory. Because I recall what I said before, if you assume that the periodicity cell is small, which goes to zero, when compared to wavelength, so if you assume that the wavelength is given, fixed, and this goes to zero, then homogenization theory applies. Then you have no band gaps, because you only have a uniform homogeneous material in the limit. The effective material applies, so the wave behaves as if it encountered a homogenized material, a homogeneous material, uniform C, constant C. In the second case, it's interesting, where the K's are comparable, they are the same order of magnitude. So here you should say that this size of the inclusions is the same order of magnitude as the wavelength. Okay. So I was explaining you that this is how we vary the wave vector, because, so I was telling you that. So you only have to analyze periodicity cell in the dual lattice, but then you can cut it in half because of the symmetries. And then the engineers, because this was in collaboration with engineers from technical, they say, you don't have to analyze the entire triangle, we only analyze the boundary. I don't have a mathematical justification for that. They are very convinced that you don't have to analyze the interior of the Brillouin triangle. You only have to look at the boundary. I'm not so very convinced. I can prove if this is true, but actually it sort of works. So here, what we see is a wave vector which goes around the boundary of the Brillouin triangle. Actually, you can see this is the first component of K. So here it increases. This is the first side of the triangle, and it is constant. This is the second side, it's the vertical or the horizontal side of the triangle, and then it decreases again. So these are the three sides of the triangle which you can see here of the Brillouin triangle. So they only analyze the boundary; they don't look inside. I have performed many tests to look for wave vectors inside the Brillouin triangle, which would violate their results, the engineer's results, and I didn't find it. So yeah, I suppose they are right. I'm not able to prove they are right. I don't know why they are right, but basically it looks like they are right. So you only have to analyze the boundary of the Brillouin triangle. And I guess that's all.
You can analyze here the plane wave, and they are isolating, so plane sound insulating materials. And if you have a space like a two-dimensional wave, depending on X and Y, not one-dimensional case, but two-dimensional case.
No, this is two-dimensional. This is two-dimensional. I say a plane wave, but it's two-dimensional. When I say a plane wave, it's for instance, yeah. This is a plane wave. K is a vector in the plane, R2, so it has direction. It could be R3 actually.
Wait, K is vector and X is the scalar.
No, X is the current coordinate. Could be R2, could be R3.
Oh, okay, so it's a.
So it's a plane wave. Imagine a plane wave in space, in three-dimensional space. So it's not one-dimensional. It's here the classification is two-dimensional, but it could be three-dimensional. But it's plane.
And that the material is sound insulated for any direction of K, actually, right?
So here, if you look at the band gap, for any K, here K goes around the Brillouin triangle. So you have a band gap for any K. Exactly. If you choose a specific direction, then you should choose just a vertical strip here. You have more gaps. If you fix the direction, or if you limit the direction of the wave, you have more gaps. So this is a gap for any direction.
Mm-hmm. And the engineer colleagues manufacture those, right? Materials.
I'm not sure about it.
You said it both epoxy and metal, so they
yes.
engineered them.
The computations were made for values of epoxy and aluminium, but yes, I think they had some others. The problem with sound is that in order to obtain band gaps, you need to have periodicity cells of size like this, big size. Because the sound, the wavelength of sound that you can hear is rather large. So you cannot build filters, acoustic filters, which are very thin. You cannot build thin acoustic filters, not with this technique. So you can build them for highways, but they are like this. You can do this for large structures, for buildings, for highways, but the size of the inclusions should be relatively large. Okay, that's a limitation. At least for sound. Now for light, it's different. Okay.
Let's end this. for, so you wrote the Maxwell's equation, so it's easy to push your method for solving light propagation problems?
I think so.
It's not
Yes, I think it's rather something known, which is known, yes. You just solve a Maxwell equation instead of this one, you just change the finite elements.
So in this particular case, you wrote homogenization doesn't work, so you just solve numerically this problem without pushing limit.
Yes, you cannot homogenize, you don't homogenize in the classical sense. It's a sort of generalized homogenization, a different way of describing the effective properties, where either the size of the inhomogeneities doesn't go to zero, it's fixed, or mathematically you can do a trick, you say it can go to zero, but then the incident wavelength goes to zero with the same speed, which is physically not interesting.
But your spectrum will survive, no? Spectrum will also be changed in a size go to zero and wavelength go to zero. Spectrum will change.
No, the spectrum doesn't change. The wave vector will change. It's not interesting because, yeah,
right?
It will go to, yes.
Okay. Other questions, Tom?
What is the trick to enlarge this band gap?
Well, first by trial and error, which is the best side about. Now we can also do something like shape optimization. You look at the shape of the inclusion, so you look here, and you say, let's do variations. And you do variations in the shape in order to, for instance, you say, I would like this eigenvalue to go down in order to enlarge the gap. So I look at this eigenvalue, I look at the configuration of the solution for this eigenvalue, and then I say, I'm looking for changes in the boundary of this inclusion, which will push this downwards. And you can do, it's very complicated, it's shape optimization. So you optimize the shape of your boundary of this inclusion in order to push this eigenvalue down, and at the same time, you want this one not to go down. Because if they both go down, it's not interesting. It's a different technique, it's possible to do.
No, it's difficult
It's
to
very
have an intuitive recipe.
Or at least not intuitive, or at least formally mathematical procedure to inverse the problem. Can you formulate it like a formally
This is an
mathematical?
inverse problem, yes. Shape optimization is an inverse problem, yes. So what I'm saying is that you can do shape optimization at the cellular. On the
Can you just
cellular.
formulate it in the form of the black box? So you do this, and you optimize it.
I haven't implemented this for Bloch waves. I did implement this for classical homogenization. So I have papers on shape optimization and topology optimization in the periodicity cell, but for classical optimization, not for Bloch waves. But it should be very similar. Now, after that, when you push this downward, it will touch here, perhaps. And then you will want to go this one and this one, both at the same time downwards. It's very difficult.
And you have infinite number of branches, right?
Yes, you have infinite number of eigen frequencies, but you only look at up to a certain limit. You only analyze the first 6 or 7. The others are not very interesting. They are too high.
Well, if you see any more questions, let's thank you again.